Hello students, this is Ashani from Cheenta.com. Today we will continue our adventure into Mobius transformation. Grab a pen and paper, let's do this together. We have already discussed this in the first video. If you have not watched it, go ahead and watch it first, okay? I'll quickly remind you, a function f is said to be multiplicative if you take two numbers m and n, suppose their GCD is 1, if f of m times n is equals to f of m times f of n, we say f is a multiplicative function. Now, sometimes it is possible to factorize a multiplicative function in terms of another function. Here is an example. And this example is a very famous problem due to Euler. What is the example? The example is like this, that suppose we have a function f which inputs n, takes the input as n and produces output as n. So f of 5 is 5. It's an identity function. F of 6 is 6. F of 7 is 7. So you can easily check that this is multiplicative. For example, f of 5 times 3 is f of 15, which is 15. And f of 5 is 5. F of 3 is 3. So f of 5 times f of 3 is also 15. It's multiplicative in a very simple way. There's nothing complicated going on here. In fact, you don't even need the GCD of m and n to be 1 in this particular case. Okay, so how can we factorize this identity function? And this is where the beautiful problem by Euler comes into place. Let's see an example. Suppose you have the number 10. And suppose you write down the divisors of 10. So these are 1, 2, 5 and 10 itself. There are 4 divisors of 10. What I'm going to do is I will write a function g which produces, it's like the Euler's totient function if you already know it. But if you don't know it, here is a definition. It takes in a number, let's say 5, and it counts the numbers which are smaller than 5 and have GCD 1 with 5. Okay, so what are those numbers? So if you take the number 5, what are the numbers that are smaller than or not exceeding 5, let's say? What are the numbers not exceeding 5, which are smaller than 5 or not exceeding 5 and have GCD 1 with 5. So 1, 2, 3, 4, all of them. They all have GCD 1 with 5. So G of 5 is 4 because there are 4 elements in this set. What is G of 10? Let's calculate. Suppose you have the number 10. What are the numbers not exceeding 10 but have GCD 1 with 10? Okay, they are 1, that's always true, 3, 7 and 9. These are the 4 numbers. So what is G of 10? You count the number of elements. There are 1, 2, 3, 4, 4 elements. So G of 10 is 4. What is G of 1? How many numbers not exceeding 1 have GCD 1 with 1? Well, that's 1, right? There are only one number, that's 1 itself. 1 itself have GCD 1 with 1 and 1 doesn't exceed 1. So obviously. What about 2? So G of 2, what is that? How many numbers are there not exceeding 2? Not exceeding 2 and GCD 1 with 2. Well, that's only one number, 1 itself. So G of 2 is also 1. Now, what we just did, let's calculate G of 1 plus G of 2 plus G of 5 plus G of 10. G of 1 is 1, G of 2 is 1, G of 5 is 4, and G of 10 is also 4. Notice that f of 10, which was the identity function, which is equal to 10, is simply equals to this sum. Isn't that wonderful? I just factorized f of 10 in terms of G of 1, G of 2, G of 5 and G of 10. So I could write f of 10 as a sum of G of 1 plus G of 2 plus G of 5 plus G of 10. That is the example. G itself, one can show, is a multiplicative function. This is in fact a homework. If you can find it out why, if you can prove it by yourself, put in the comment section. Why is the function g a multiplicative function? But more interestingly, you can factorize f in terms of g, which is kind of amazing, isn't it? The Mobius inversion says that if you can factorize f in terms of g, then you can factorize g in terms of f. That is the Mobius inversion formula. We are not there yet, but the question is, why does it work? Will it always work? So here is a little sort of a exercise. Try this with 35. That is, check f of 35, is it equal to g of the divisors of 35? You write down the divisors of 35, you calculate it, and you tell me if it works. Can you put it in the comment section? And then, can you give me a proof of why this factorization will always work? We recently put out a very interesting book in a dialogue format. It is called An Invitation to Mathematical Olympiads and Research. You can see the image of the front page of the book in this video, I guess. If you are interested in this sort of discussions and also how you can think about mathematics, not only learn math but how to think about it, maybe you can get a copy of the book on your own. I'll continue this discussion in the next video. Until then, keep on doing great problems. Thank you for watching. Bye.